Hello, and welcome to this presentation on trigonometric identities. Trigonometric identities, or trig-IDs for short, occur in a wide array of topic areas, such as the calculus, where we're trying to derive formulae or integrate expressions and solve differential equations. At this high-level study, it's often useful to rewrite expressions in alternative forms to help simplify them, and trig identities allow for that. Trig IDs occur within computer graphics packages, mobile phone design, when combining AC waveforms together, or in the solution of trigonometric equations. This slide just shows an overview of trigonometric identities. There are 6 trigonometric identities we'll be interested in to begin with: the sine theta, cos theta, and tan theta, which we're probably familiar with already. Then also we'll look at the cosecant theta, the secant theta, and the cotangent theta. We'll derive those in a moment. There are other trig identities that occur in practice: sum or difference of 2 angles, or the sum and product formulae. We will not be looking at these in this presentation. Other trig identities include double angle formulae, half angle formulae, and the ones that we're going to concentrate on here is the Pythagorean identities. I've also highlighted here this function, the cos squared theta equals to a half 1 plus cos 2 theta, and in the example over the page I'm going to show you how I use this within a calculation to simplify an integral. Some of you may want to skip the next few slides because I'm just going to outline a problem I was involved with in industry many years ago, in which I used a trigonometric identity to simplify an integral. This exercise related to the design of a chimney stack that was 26 meters high. The chimney stack was 2.2 meters in diameter and a 12.5 millimeter wall thickness. It was made of stainless steel. Within the stack there are 3 flues that run the full length of the chimney stack. What the customer wanted to do was to put some manhole covers at the bottom of the chimney stack here and here. In other words, take away material from the chimney stack at that location. If you understand engineer's bending theory, this is the worst place you can remove the material, because this is where the maximum bending stress would occur, at the base of the stack. So what this calculation endeavours to do is to find the secondary moment value of the chimney stack at this base section with those cutouts for the manholes in position. We calculated the area at the base of the chimney stack based on thin walled theory here, because of a very thin section compared to the diameter. We knew the angles of the cutout, we knew the radius, and we used the thickness of the chimney stack. Within the analysis, I only used half of the cylinder section due to symmetry, because I could just double the value to get the total secondary moment. Those of you that understand engineer's bending theory will know I need to find the neutral axis in this position because it shifts due to the cutouts in the tube section. And to do this I need to find the first moment of area of the section. I've used here integration to do this. I'm just modelling half of the tube section, so that's why the 2's are here, and I'm just integrating the section with respect to the x-axis shown above to find the first area moment. To find the first area moment was a fairly straightforward integration process. I knew my y in terms of my geometry in this case, which is r take away r cos phi, and I knew my area. Again, assuming thin walled section, that would be RT times d phi on the previous page. The integrals here are all standard form. I could integrate these functions 1 and cos phi. So I solved my integral for the first area moment, quite straightforward because it's standard form, and knowing the angles beta, gamma, the radius and the thickness, I could work out what the first area moment was, and knowing the original area in the question, I could work out the y bar, the shift of the neutral axis effectively. Now I needed to work out the second area moment, because I need this for the engineer's bending theory. So the second area moment is a similar kind of calculation, a similar integral, except I have to square the y value. So my second area moment here involves the squaring of this bracket here, the r cos phi take away h. When you square that, you end up with a cos squared phi term in the expansion. And this is where my problem occurred. I didn't have an integral for cos squared phi. But using a trig identity replacing the cos squared phi with the 1 plus cos 2 phi, which is a trig identity if you look at the previous slides, I was then able to make it into standard form, and now I could integrate it. I could integrate the 1 and I could integrate the cos 2 phi with respect to phi. So what I'm trying to show with this illustration is that this complex problem we're reviewing came to a halt when I couldn't integrate the cos squared phi, but knowing the trig identity and rewriting cos squared phi using the trig identity allowed me to then proceed with the calculation and solve the problem. Calculations continued over here. It's quite a lengthy calculation, but all because I could use a trig identity, I was able to progress the calculation on further. Eventually I work out my second area moment for the chimney stack, and then I could find my bending stress at the base of the stack. We're now going to review trigonometric ratios. There are 6 definitions for trigonometric ratios to be aware of in any right-angled triangle. 3 you're probably familiar with already, and 3 might be new to you. We're going to apply Pythagoras' theorem to the right-angled triangles we'll be reviewing. Don't forget Pythagoras' theorem states that the hypotenuse is equal to the square root of the opposite side squared plus the adjacent side squared. In my triangle here, I've given my angle theta here, so the opposite side would be over here, opposite the angle. The hypotenuse is always the longest side, opposite the right angle, and the remaining side is called the adjacent side. From previous work, we've probably come across the SOHCAHTOA, a mnemonic. It's a way of remembering the trigonometric ratios. The sine of the angle is the opposite over the height, that's the SOH part. The cos of the angle is the adjacent over the hypotenuse, that's the CAH part. And the tan of the angle is the opposite over the adjacent, that's the TOA part. These are pre-programmed into our calculator, and we're probably quite familiar with using those at this level. Also note from previous work, the definition of tan theta is sine theta over cos theta, and that's a very useful definition to be aware of in this work. There are 3 other functions we need to be aware of, and these are reciprocals of the sine, cos and tan functions. The first one is cosec theta, which is actually 1 upon sine theta, the reciprocal of sine theta. And that's hypotenuse over the opposite side. Cosec is short for cosecant. The next one is sec theta, which is the reciprocal of the cos function. That's hypotenuse over the adjacent side. Sec is short for secant. Finally, we've got the cot function. That's the reciprocal of the tan function. So that's adjacent over the opposite side. Cot is short for cotangent. These functions are not usually built into your calculator, so we have to evaluate them from their definitions above. So a trigonometric identity is an expression that is true for all the values of the unknown variable, be that x, theta, t, whatever it's going to be. So the listing below are all trig identities. What we're going to do now is to prove some trig identities. These are called Pythagorean trig identities. They all come from the right angled triangle. I'm going to go through the proof to get the bolded box expression. So the first trig ID we'll look at is derived as follows. From the above diagram, we know that the opposite side squared plus the adjacent side squared is equal to the hypotenuse side squared. That's Pythagoras' theorem. If I divide throughout by the hypotenuse squared, I get opposite squared upon hypotenuse squared plus adjacent squared upon hypotenuse squared is equal to the hypotenuse squared upon hypotenuse squared. Dividing throughout by hypotenuse squared here. Looking at the first term and noting that sine theta is opposite over hypotenuse, then opposite squared over hypotenuse squared is actually sine theta squared. Looking at the second term, I've got adjacent squared upon hypotenuse squared. That would actually be cos theta squared. And looking at the right hand side, hypotenuse squared upon hypotenuse squared is 1. So my first trig identity I've proved, this Pythagorean identity, is sine squared theta plus cos squared theta is equal to 1. And don't forget the variables can change. That could be sine squared x plus cos squared x equals to 1. Second trig ID we'll prove from Pythagoras' theorem. We start again with the opposite squared plus the adjacent squared equals hypotenuse squared, but this time we divide throughout by the adjacent squared. So each term is now divided by adjacent squared. So I get opposite squared upon adjacent squared. Now if you think of your definitions, opposite upon adjacent is tangent. So I've actually got tangent squared here, plus adjacent squared upon adjacent squared, that cancels to give me 1, so that's plus 1 on the left hand side. And on the right hand side, I've got hypotenuse squared upon adjacent squared. Now that's actually going to be the reciprocal of the cos function. And from previous slides, that would be sec. So in this case, I get sec squared theta. So I've got an identity here of tan squared theta plus 1 is equal to sec squared theta, where sec squared theta is 1 upon cos squared theta. Okay, our third trig identity here from Pythagoras' theorem. What we're going to do now is divide throughout by the opposite side squared. So taking the first term on the left hand side, I get opposite squared divided by opposite squared, that gives me 1. Taking the second term, I get the adjacent side squared divided by the opposite side squared. Now if you think that the tan function is opposite over adjacent, we've got here the reciprocal function, so we've got the cot function and it's squared. So I add cot squared theta to our expression. On the right hand side, I've got the hypotenuse squared divided by the opposite squared. And again, if you think of opposite over hypotenuse is a sine function, so hypotenuse over opposite is the reciprocal, and that's the cosec function. So I get cosec squared theta on the right hand side. And there's my third trig identity we're going to use. Okay, on this side we just produce a summary of all the previous trig identities. Just notice that these first two lines here are really the same trig identity, just split into two different forms. The first form is sine squared theta, can be shown to be 1 minus cos squared theta, and cos squared theta can be shown to be 1 minus sine squared theta. They've been shown that way because often they're used that way, but they both relate to the sine squared theta plus cos squared theta equals to 1 identity. The next two identities are just rearrangements of the proofs on the previous page. So tan squared theta can be shown to be sec squared theta minus 1, and cot squared theta can be shown to be cosec squared theta minus 1. Also shown here are the definitions of cosec theta, which is 1 upon sine theta, of sec theta, which is 1 upon cos theta, cot theta, 1 upon tan theta, and don't forget that tan theta is sine theta upon cos theta, and then cot theta is the reciprocal of tan, which is cos theta upon sine theta. Also note for reference that sine squared theta actually means sine of theta or squared. The conventional way to write it is sine squared theta, but it actually means sine of the angle or squared. The rest of the presentation now looks at work problems on trig identities. What we're going to do is prove the identities. This is something we don't normally do in technician engineering work. We don't do a lot of proving as such, so a slightly different approach here. We're going to prove identities. We're given identity and we're going to prove that the left hand side equals to the right hand side. You can start with either side, but I'm going to start with the left hand side and prove it's equal to the right hand side. Now in the listing below, I've tried to illustrate some tips and wrinkles that may be useful in helping us solve the problems we're going to look at. These in themselves at the moment may not make much sense to you, but I'm going to try and give you this little toolbox and we're going to apply this to all the problems as we need to as we go through the presentation. So I'm hoping it will make more sense as you start to see the worked examples. So for the moment, bear with me. I'm just going to outline these tips and wrinkles. So all the following just relate to ways we can manipulate equations to simplify them into the formats we're trying to find. Item 1 here. Sometimes we might want to change the trigonometric ratios into different forms, into their definitions maybe. So for example, if you were given something like cosec theta times by cot theta, you could write that in its definition of 1 upon sine theta, which is the cosec theta, multiplied by 1 upon tan theta, which is the cot theta. And sometimes that will simplify the problems you're looking at and help you progress a solution. Next item, sometimes factorising may help. So for example, 1 plus tan theta could be factorised as tan theta outside the bracket, 1 over tan theta plus 1. If you expand the bracket, you get back to the left-hand side. Sometimes that helps in simplifying problems. Item 3, sometimes inserting trig identities will help. So for example, with this expression, you've got cos squared beta, take away tan beta, plus sine squared beta. Well, we know from our trig identities that cos squared beta plus sine squared beta is equal to 1. So I could replace those two terms with 1 and leave myself with the minus tan beta. I've simplified the expression. Item 4 here, sometimes multiplying the top and the bottom by the same term simplifies our expressions. So 1 minus sine theta divided by 1 plus sine theta. If I was to multiply the top and bottom by 1 minus sine theta, I do not affect the expression, but sometimes this will actually help me simplify my solutions. Continuing on here, my little toolbox of tips and wrinkles. Sometimes reducing higher powers helps. For example, if you're given a sine cube x function, there are no sine cube, no cos cube, etc. in the trig identity we're using. So we could simplify that as sine x multiplied by sine squared x, because we do have a trig identity for sine squared x. Item 6 here, sometimes expanding brackets help. So given 1 plus sine a, there's no trig identity for 1 plus sine a I can use. So 1 plus sine a squared is as it is, I can do nothing with that. So sometimes expanding the bracket may help me simplify the terms. So 1 plus 2 sine a plus sine squared a when you expand the bracket. Sometimes that will help simplify the problem, because 1 plus sine a itself cannot be simplified. Item 7 here, sometimes using common denominators will help. So in this left-hand side, I've got sine squared theta over cos theta plus sine theta cos theta, effectively over 1 there. If we want to put that into a common denominator of cos theta in this case, I can simply write the sine squared theta over it, but I've got to add the plus the sine theta times by cos squared theta now. But by doing that, I can write it over a common denominator. And sometimes that will help simplify the solutions. Item 8 here, sometimes resolving into partial fractions can be helpful. So given sine beta, take away cosec beta all over cos beta, I could write that in partial fractions form as sine beta over cos beta, take away cosec beta over cos beta. So the cos beta is a common factor there. Sometimes resolving into partial fractions will help us simplify our problems. And the final one, 9 here, it's worth noting that sine squared x take away cos squared x is the same as sine x plus cos x in brackets times sine x minus cos x. And again, there are occasions when that relationship is useful. In the examples we're going to look at now, we're going to prove various identities showing that the left-hand side is equal to the right-hand side. And I'll use different parts of my toolbox to help me do that. So in the first example here, we're asked to prove the identity of sine squared theta times cot theta times sec theta is equal to sine theta. So I'm going to start with the left-hand side of the expression and prove it's equal to the right-hand side. From my toolbox, I'm going to use the changing geometric ratios into their sine theta and cos theta terms to help me solve this. So that's a little hint for us. We take the left-hand side. I've got sine squared theta multiplied by cot theta multiplied by sec theta. So what I'm going to do here is replace the cot theta and the sec theta with their definitions. So cot theta is cos theta over sine theta, and sec theta is 1 upon cos theta. That's from our previous work. What you notice here is we can start cancelling terms down. If you look at the cos theta term, if I just cancel this for us, I could cancel this value with this value, so they cancel to give me 1, and I could cancel the sine theta value with the squared on the sine there to leave me with sine theta. So I end up with sine theta on the left hand side, which is what I'm trying to show. Example 2 here, we're asked to prove in this case that tan x plus sec x all over sec x multiplied by, in brackets, 1 plus tan x over sec x is equal to 1. Now this is a question where we're going to expand the brackets and simplify. So again, taking the left hand side only, I'm given tan x plus sec x is divided by sec x multiplied by, in brackets, 1 plus tan x divided by sec x. So what I'm going to do first of all is multiply out the denominator. So sec x times 1 is sec x, and sec x times tan x over sec x, can you see that the sec x will cancel here, leaving with the plus tan x? Just think that through for yourself. Sec x times the tan x divided by sec x will cancel, even with tan x. When you look at it now, I've got the same term on the top as I have on the bottom, so they cancel to give me 1. So I prove the left-hand side equals to the right-hand side. Example 3 here, we've got to show that 1 plus cot theta divided by 1 plus tan theta is equal to cot theta. I'm going to use a factorising denominator approach here. Again, taking the left-hand side only, I start with 1 plus cot theta over 1 plus tan theta. On the bottom line, I will factorise on tan theta, so taking tan theta outside of a bracket, inside I get 1 divided by tan theta plus 1. Think that through to yourself. If I expand the bracket again, I get tan theta times 1 over tan theta. That will cancel to 1, and tan theta times the 1 would be tan theta. So I factorise the denominator. Now looking at what I've got here, the top line and the bottom line here are the same, so they can cancel. I literally cancel the 1 plus cot theta on the top with the 1 plus cot theta on the bottom, and that leaves me with 1 upon tan theta. Don't forget 1 upon tan theta is actually cot theta. So again, I've proved the right-hand side is equal to the left-hand side. Example 4 here, we're asked to prove that cos squared theta minus sine squared theta is equal to 1 minus 2 times by sine squared theta. I'm going to do this by inserting a trig identity. So again, taking my left-hand side, I'm given cos squared theta minus sine squared theta. I'm going to use a trig identity here of the cos squared theta plus sine squared theta equals to 1, which can be arranged as shown previously as cos squared theta equals to 1 minus sine squared theta. So replacing the cos squared theta with the 1 minus sine squared theta, so that bracket there replaces the cos squared theta above, I get 1 take away sine squared theta, take away sine squared theta. So that's basically 1 take away 2 sine squared theta, and again I've shown that the left-hand side is equal to the right-hand side. Example 5, a slightly more complicated example here. We're given 1 minus sine x divided by 1 plus sine x, all to the half, don't forget the half as a square root, can be shown to be equal to sec x take away tan x. So what we're going to do here is multiply the numerator and denominator by the same term. So in this particular case, I'm going to multiply the top and bottom here by 1 minus sine x. So there's my original expression, the 1 minus sine x over the 1 plus sine x, but I'm multiplying top and bottom by 1 minus sine x and 1 minus sine x. So I don't affect the actual question. It's like multiplying the top by 2 and the bottom by 2, so I don't affect the overall problem. But when I expand it, I will find that I will get something in the form that I can now simplify. So on the top, what you get is 1 minus sine x all squared, 1 minus sine x times 1 minus sine x. And on the bottom, when you expand, you get 1 plus sine x minus sine x minus sine squared x. That's the expansion of the bottom line. That simplifies. On the top, I get 1 minus sine x all squared, and on the bottom, I get 1 minus sine squared x. The positive sine x and the negative sine x cancel. Example 5 continued here, repeating this line for convenience. So I start with 1 minus sine x all squared on the top line, and on the bottom I've got 1 minus sine squared x. Don't forget it's all to the power of a half still here. On the bottom line now, again noting that cos squared x is equal to 1 minus sine squared x for my trig identities, I can replace the denominator by cos squared x. If I now square root the top and the bottom, I will get 1 minus sine x on the top, because I square and the square root there cancel each other. If you look at your third law of indices there, it's 2 times a half is 1. And on the bottom line, square rooting, I get cos x. Now I can put them into their partial fractions here, so I get 1 upon cos x, take away sine x upon cos x, because cos x is the common denominator here. So resolving into partial fractions. I get now sec x, because 1 upon cos x is sec x, take away tan x, because sin x upon cos x is tan x. And that proves the left-hand side equals to the right-hand. What we're going to do now is look at some exercises where we're going to prove, again, the left-hand side equals to the right-hand side of identity, and using all the tips and wrinkles that we've had in the previous slide. In each of the questions there will be hints to give you an overview of the process involved here. So taking the left-hand side of the expression here, I'm given cos cubed beta over cos beta plus sine beta times cos beta. And the first thing I'm going to do is write them over the common denominator of cos beta. So the first term is fine, the sine cubed beta is over cos beta, so I just write that as sine cubed beta. But then I have to add sine beta times cos squared beta. Notice cos squared beta. Because I'm writing this second term over cos beta, I need the cos squared term so it cancels with the cos beta on the bottom. I mustn't change the equation or the question I'm given, and I haven't in this case, because cos squared beta over cos beta is still really cos beta on the top line. Just think that through for yourself. Make sure you understand that step I've used there. What I've done on the next line is write the cos cubed beta in terms of sine beta times sine squared beta. I notice in none of my trig identities do I have a sine cube term or cos cube term, so I'm going to write it in terms of a sine beta times the sine squared beta, because I do have a sine squared beta term, and that might be useful in a moment. The rest of the terms apply, plus sine beta times cos squared beta over cos beta. So exercise 1 here continued. So just repeating this line from the previous slide, sine beta times sine squared beta plus sine beta times cos squared beta is all over cos beta. What I can do now is factorise on the top line. Notice that sine beta is common to both terms, so I can take a sine beta outside of a bracket, and inside I can put sine squared beta plus cos squared beta. That's still over cos beta. Noting the trig identity that sine squared beta plus cos squared beta equals to 1, I can replace the bracket simply by 1. So on the top line I get sine beta over cos beta. We know that sine beta over cos beta is tan beta, so I've now shown the left-hand side equals to the right-hand side. Exercise 2 here, I'm asked to show that tan theta plus 1 over tan theta is actually 1 upon sine theta cos theta. I'm going to use here a common denominator first of all, and then insert a trig identity. That's the hint. So from the left-hand side, tan theta plus 1 upon tan theta is my starting point. I'm going to write tan theta in terms of its definition. So tan theta is sine theta over cos theta. And on the next term I've got 1 over, and again tan theta is sine theta divided by cos theta. On the next line I've simply rewritten the second term up the other way. 1 upon sine theta upon cos theta is actually cos theta over sine theta, simplifying its format there. That goes back to fractions, division of fractions. On the next line what I've done is make a common denominator of the cos theta sine theta term. So it means on the top line I must have sine theta times a sine theta, cancel the sine theta on the bottom, plus a cos theta times a cos theta to cancel the cos theta on the bottom. On the next line I get sine squared theta plus cos squared theta, just tidying up the terms, over sine theta cos theta. Again, noting from our trig identity, sine squared theta plus cos squared theta is equal to 1. So on the top line I get 1 over sine theta cos theta. And that's what I was asked to prove. Exercise 3, we're asked to show that sine alpha plus cos alpha all squared is equal to 1 plus the 2 sine alpha cos alpha. So looking at the left-hand side here, sine alpha plus cos alpha in the brackets cannot be simplified. I have no trigonometric identity that would replace sine alpha cos alpha. I have a sine squared alpha plus cos squared alpha trig identity, but that's not what I've got here, because I've got sine alpha plus cos alpha all squared, and that's different. So all I can think to do here is to try and expand the brackets. So sine alpha plus cos alpha squared is sine alpha cos alpha times by sine alpha cos alpha. If you expand the brackets, you get sine squared alpha plus sine alpha cos alpha plus cos alpha sine alpha plus cos squared alpha. I'll let you do the expansion and check that for yourself. Simplifying the terms, I get sine squared alpha plus 2 times sine alpha cos alpha from the previous line above, plus the cos squared alpha. Noting that sine squared theta plus cos squared theta equals to 1 from our trig identity, in this case our sine squared alpha plus cos squared alpha can be replaced with the 1. And that's what I've done here. This 1 replaces the sine squared alpha plus cos squared alpha term, but even with the plus 2 sine alpha cos alpha. And again we've proved left hand side equals the right hand side. Exercise 4 here, we're asked to show that cot theta plus tan theta is equal to sec theta times cosec theta. Don't forget sec theta is 1 upon cos and cosec theta is 1 upon sine. So the hints here to use trig definitions, find a common denominator, insert a trig identity. On the left hand side I've got cot theta plus tan theta. I'm going to put their definitions in. Cot theta is cos theta over sine theta, plus tan theta is sine theta over cos theta. On the next line I'm making a common denominator of sine theta cos theta, sine theta times cos theta. So on the top line I need to have cos theta times a cos theta plus a sine theta times a sine theta. And I'll let you check that through as to how I've written that numerator there. On the next line I get cos squared theta plus sine squared theta in the numerator over sine theta cos theta. Exercise 4 here, I've just repeated the top line for convenience here. So cos squared theta plus sine squared theta all divided by sine theta times cos theta. If we notice on the top line that cos squared theta plus sine squared theta equals to 1 from our basic trig identity, I can replace the top line, the numerator, with 1. On the bottom line I get sine theta times by cos theta. If I split that into two terms to make it easier to understand what's going on here, I get 1 upon sine theta multiplied by 1 upon cos theta. That's the same as the previous line, just rewriting the expression. If we now notice that cosec theta is 1 upon sine theta and sec theta is 1 upon cos theta, I can now replace the 1 upon sine theta with cosec theta, and that's multiplied by the 1 upon cos theta is now sec theta. If you look at the original expression, we've now proved that the left-hand side equals the right-hand side. Exercise 5 here, we're asked to show that 1 plus sec a in a bracket and multiplied by 1 minus cos a in another bracket is equal to sine of a times by tan of a. So here, looking at the left-hand side again, I've got 1 plus sec a in my bracket multiplied by 1 minus cos a. Now I can't do anything to simplify the brackets. There's no trig identities, no rearrangement I can do within the brackets at all. So all I'm going to do here is expand the brackets and see where that takes me. So expanding the 1 plus sec a multiplied by 1 minus cos a, I get 1 minus cos a plus sec a minus sec a times cos a. I'll let you have a look at that to follow the expansion through. If we notice that sec a is equal to 1 over cos a from our definitions, then we can rewrite the equation as 1 take away cos a plus 1 divided by cos a take away cos a upon cos a. Just follow that last term to make sure you understand that. We're writing the sec a as 1 upon cos a. On the next line then we can simplify. We get 1 minus cos a plus 1 upon cos a, and the cos a upon cos a becomes 1, so it's negative 1. Now we can see we've got a positive 1, a negative 1, then we can simplify that by saying that's minus cos a plus 1 upon cos a. In other words, the plus 1 and the minus 1 cancels. Exercise 5 continued. I just repeated this line for convenience, so minus cos a plus 1 upon cos a was from the previous slide. Now what I'm doing now in the next line is making a common denominator of cos a for both terms. So I need to write the first term as minus cos squared a over the cos of a. I need the cos squared to cancel with cos a on the bottom, plus my 1 upon the cos a. On the next slide, I just simply rearrange the equation, put the positive term in front of the negative term, so 1 minus cos squared a upon cos a. If we now go back to our standard trig identities, we know that sine squared a can be written as 1 minus cos squared a from our previous work. So I can now replace the top line, the numerator, with sine squared a for the 1 minus cos squared a. Don't forget that sine squared a is actually sine a times sine a, so I could write the numerator as sine a times sine a all over cos a. And then again, noting that tan a is sine a over cos a, I can simplify to sine a multiplied by sine over cos gives me a tan a. So I've concluded that the left-hand side equals the right-hand side. Okay, exercise 6 here. We're asked to show that cosec beta minus sine beta, all divided by cosec beta, is equal to cos squared beta. Just for reference here, the cosec betas on the left-hand side, top and bottom, do not cancel here because we don't have a cosec beta against the sine beta. So just be careful of that. Some students think they can cancel the cosec betas, but you cannot in this case. So we need to start from the left-hand side equals to cosec beta minus sine beta, all divided by cosec beta. First thing I'm going to do is write into partial fractions here. So cosec beta over cosec beta, take away sine beta over cosec beta. The cosec beta was a common denominator in the previous line, and I've just written into partial fractions there. Obviously cosec beta divided by cosec beta is 1, so that's 1 take away the sine beta over the cosec beta. If we notice that cosec beta is actually 1 divided by sine beta, and I can write the denominator over here as 1 divided by sine beta for the cosec beta. Exercise 6 continue, just repeated this line for convenience. So 1 take away sine beta divided by 1 divided by sine beta. Now this is a fraction problem here, just be careful how I manipulate the equation. I get 1 take away, I've got sine beta over 1 divided by 1 upon sine beta. Now that's the way we deal with division of fractions. We turn the second fraction upside down and multiply if you go back to your fractions work. So I've done the same thing here, but it's with trigonometric terms here. So that gives us on the next line 1 take away sine beta over 1 multiplied by sine beta over 1. So I'm changing my division sign to a multiplication sign and inverting the fraction there. Next line I get 1 take away sine beta times sine beta, or if you like 1 take away sine squared beta. And again, if we go back to our tables of the trig identities, we notice that cos squared beta is 1 take away sine squared beta. So in this case, we've proved the left-hand side equals the right-hand side as cos squared beta. Exercise 7 here, we're asked to show that sine of gamma over 1 minus cos of gamma is equal to 1 plus cos of gamma over sine of gamma. So just a different variable there, gamma, instead of the thetas and a's, etc. we've used before. So looking at the left-hand side here, I get sine gamma over 1 minus cos gamma. What I'm going to do here is apply a little tip and wrinkle of multiplying top and bottom by the same term here, and I'm going to use the 1 plus cos gamma on top and bottom here. I do not affect the equation by doing this, but you'll see in a moment I do simplify and it helps me solve this problem. So I get sine gamma on the top multiplied by 1 plus the cos gamma, and you must have a bracket there, by the way. You must keep it in brackets on the top line there. On the bottom I've got 1 minus cos gamma. Notice again I put a bracket around that, times by 1 plus cos gamma. Okay, so basically what I've done there is multiply top and bottom by the change of sign of the denominator. The denominator is 1 minus cos gamma, and I've multiplied top and bottom by 1 plus cos gamma. On the next line I get sine gamma multiplied by the 1 plus cos gamma in the brackets. On the bottom I've expanded the brackets. Again, take care with the expansion. You get 1 plus cos gamma minus cos gamma plus cos squared gamma. Exercise 7. Just repeat this line for convenience. I've got sine of gamma multiplied by 1 plus cos gamma for the numerator, all divided by 1 plus cos gamma minus cos squared gamma on the bottom line. The bottom line simplifies because we've got a cos gamma take away a cos gamma, so that will go to 0. So on the bottom line we simply end up with 1 minus the cos squared gamma. The numerator remains the same. Now from our trig identities we know that sine squared theta is equal to 1 minus cos squared theta, or in this case sine squared gamma equals 1 minus cos squared gamma. So we can replace the denominator by sine squared gamma. The numerator remains the same. Now what I'm doing on the next line is to simplify top and bottom. Essentially I'm cancelling this sine gamma on the top line with the squared on the sine gamma on the bottom line. So on the top line I will now get just a bracketed term of 1 plus cos gamma, that's what's inside the bracket, and that's all divided by sine gamma. And that's now proved that the left-hand side equals to the right-hand side. Exercise 8, we're asked to show that sine y over 1 plus cos y plus 1 plus cos y over sine y simplifies to 2 over sine y. So again, taking the left-hand side of our equation, we get sine y over the 1 plus cos y plus 1 plus cos y over sine y. And what I'm going to do here is bring them together under a common denominator. So the denominator is going to be 1 plus cos y, notice that's in brackets, multiplied by sine y. You must have the brackets around the 1 plus cos y. So on the top line now I'll get sine y times sine y, because I need the sine y on the top to cancel the sine y on the bottom, plus 1 plus cos y multiplied by 1 plus cos y. And again, I need that extra 1 plus cos y on the top to cancel with that on the bottom. I mustn't affect the original question when I bring my terms together over a common denominator. And if you look at that carefully, I haven't. On the next line, just simplify and I get sine squared y, that's the sine y times the sine y, plus the 1 is expanded in the brackets now, plus the 1 plus the cos y plus cos y plus cos squared y. I've just expanded the 1 plus cos y times 1 plus cos y there. That's over 1 plus cos y times sine y. Again, I would encourage you to look at that very carefully and think through the steps involved. Okay, exercise 8 continued. Just repeated the top line here for convenience. So we get sine squared y plus 1 plus cos y plus cos y plus cos squared y, all divided by 1 plus cos y multiplied by sine y. So what we're going to do now is simplify the above expression. Noting that sine squared y is equal to 1 minus cos squared y, I could replace the sine squared y in the line above with the 1 minus cos squared y here. Also noting that cos y plus cos y is 2 cos y, I can simplify the top line here with my plus 2 cos y. If I then collect the terms together, I've basically got 1 plus 1 from the 1 from the bracket and 1 here, plus my 2 cos y, and notice the minus cos squared y and the plus cos squared y will cancel each other out on the top line. So on the top line it simplifies to 2 plus 2 times cos y, all divided by denominator of 1 plus cos y times sine y. If I factorise on the top line on 2, I now get 2 outside of a bracket of 1 plus cos y, and on the bottom line I've got the 1 plus cos y times the sine y. Here we can see that the brackets cancel on the top. I can cancel this 1 plus cos y with this 1 plus cos y to give me 1. So I end up with 2 divided by the sine of y, which proves the right hand side here. Okay, exercise 9. We're asked to show that sine theta divided by 1 minus cot theta plus cos theta divided by 1 minus tan theta can be simplified to sine theta times cos theta. So taking the left hand side, we start with sine theta over 1 minus cot theta plus cos theta over 1 minus tan theta. What I'm going to do here is multiply the first fraction by sine theta top and bottom. So I don't affect the fraction, but you'll see in a moment this will help me simplify this function. And with the second fraction, I'm going to multiply top and bottom by cos theta. And again, I'm not affecting the fraction, but in a moment that will help me simplify the problem. So on the next line, I get sine squared theta on the top, tidying up the sine theta times the sine theta, and that's divided by, if I expand the bracket, sine theta minus sine theta times cot theta. Again, that's just expansion of a bracket. Sine theta times 1 is sine theta times minus cot theta is minus sine theta cot theta. I add to that the next term, which is cos squared theta, so cos theta times cos theta, all divided by cos theta minus cos theta times tan theta when I expand the bracket on denominator. Now recalling the definitions here of tan theta is equal to sine theta divided by cos theta, and cot theta, which is 1 upon tan theta, is cos theta divided by sine theta. I'm now going to insert them into the above line. So I get now on the first term sine squared theta divided by the sine theta take away sine theta multiplied by not cot theta but cos theta divided by sine theta. And as you can see there, I can cancel the sine thetas top and the bottom of that denominator. Add to that the cos squared theta divided by cos theta take away cos theta times by this time the tan theta, which is now sine theta divided by cos theta. And again you can see I've cancelled out the cos theta terms on that denominator. So that line now simplifies to sine squared theta all divided by sine theta minus cos theta for the first fraction plus cos squared theta divided by cos theta minus sine theta for the second fraction. I would encourage you to work through that on your own. Think each step through very carefully because the fractions in the expansion of the brackets can cause problem with understanding. Exercise 9 continued. I'll just repeat this line for convenience. I've got sine squared theta divided by sine theta minus cos theta plus cos squared theta divided by cos theta minus sine theta. Now the denominators are actually very similar between these two fractions, but it's just that there's a change of sign on the second one in that the cos theta minus sine theta is reversed to the sine theta minus cos theta in the first fraction. So what I'm going to do is make those denominators the same, and I can do that by, on the second fraction, changing the order of the functions. So instead of having cos theta minus sine theta, I'm going to have sine theta minus cos theta. I've effectively multiplied the bottom line there by minus 1 to do that. But of course that then affects the overall equation. So what I need to do is multiply the top of the fraction by minus 1. And that's why I get a change of sign here. So overall now I've still got the same problem, but I've managed to make my denominators, both fractions, the same. I would suggest you think about those two lines and the little change I've made on that second fraction to bring the denominators to the same values. What I can do now on the next line is bring the terms together because they've both got the same common denominator. So I can simply write on the top line sine squared theta minus cos squared theta. Now noting from our previous work that a sine squared x minus cos squared x can be written as sine x plus cos x multiplied by sine x minus cos x. That's something we had in our dips and wrinkles page a few slides previously. So noting that relationship, I can now change the top line of my fraction from sine squared theta minus cos squared theta to sine theta plus cos theta multiplied by sine theta minus cos theta. The denominator remains the same. And what you notice on the next line is I can now cancel my sine theta minus cos theta on the top line with sine theta minus cos theta on the bottom line. And that simply leaves me then with sine theta plus cos theta, which is what I was trying to prove. Again, I would strongly encourage you to go back through that slide and try and understand these are the steps we use there to get to the final solution. Okay, so in this presentation we've looked at this little toolkit of methods that might help us solve these trigonometric identity problems, and we've gone through an array of different examples to try and show how we apply these various tools and techniques to solve problems. What I would strongly encourage you to do now is to attempt the questions shown here, apply the tools and techniques we've used on the previous slides in the previous examples to try and show how the left-hand side equals to the right-hand side. I wish you well with your endeavours. Bibliography here of the reference sources that have been used, some excellent texts here that have been used to help develop this presentation. I hope this presentation has been helpful to you. Thank you for viewing.